In a sealed laboratory beneath the Swiss Alps, a beam of light did something it was never supposed to do. It arrived before it left. Scientists ran the test again and again. The numbers refused to behave. Tonight, we step inside the experiment that cracked one of physics' oldest rules. We'll witness photons moving faster than the universal speed limit, particles whispering across impossible distances, and a single measurement that may rewrite everything Einstein built. If cosmic mysteries like this pull you in, hit that like button and subscribe so you never miss another journey into the unknown. Take a deep breath. Reality is about to get stranger. Every piece of technology you've ever touched runs on one number: your phone, your microwave, the satellites spinning above your head at this very moment. They all depend on a single cosmic speed limit that physicists treat as sacred. That number is the speed of a light, roughly 186,000 miles every second. Fast enough to circle the Earth 7.5 times in the time it takes you to blink. For over 100 years, this number has been the backbone of everything scientists understand about reality. Albert Einstein built his entire theory of relativity on it. He declared that nothing, absolutely nothing, could travel faster than light through empty space. Not a rocket, not a signal, not even information itself. Physicists call this the universal speed limit, and it holds the cosmos together like invisible stitching. Think of it this way. Imagine a highway with one unbreakable rule. No car, no matter how powerful, can exceed a certain speed. Now imagine that rule is not made by police, but by the fabric of space itself. Break it, and causality falls apart. Effects could happen before their causes. You could theoretically send a message to yesterday. That is why this speed limit matters so much. It is the wall that keeps time flowing forward. Einstein's rule has been tested thousands of times, in particle accelerators, in deep space observations, in laboratories across every continent. Every single test confirmed the same thing. Light always wins the race. Nothing catches it. Nothing beats it. Nothing even comes close. Until recently. In the past few years, a handful of experiments have started producing results that scientists cannot explain. Results that, if taken at face value, suggest the speed of light may not be the hard wall Einstein described. Something is slipping past it. Something is bending the rule in ways that should be physically impossible. These are not fringe experiments run by amateurs. These are measurements taken by teams at some of the most respected research facilities on Earth: CERN in Switzerland, Gran Sasso in Italy, national laboratories in the United States and Japan. The researchers running these tests checked their equipment. They repeated the experiments. They brought in outside teams to verify everything, and still the anomalies remained. Something was moving faster than light. Or at least something appeared to be. The implications are enormous. If the speed limit can be broken, even slightly, then the entire foundation of modern physics starts to wobble. Time travel becomes a scientific possibility rather than a fantasy. Communication across vast cosmic distances could happen in an instant. The universe might be far stranger than anyone ever imagined. Most scientists still believe these anomalies will eventually be explained by measurement errors or overlooked variables. That is how science tends to work. Extraordinary claims require extraordinary evidence, and so far, no one has been able to fully nail down what is happening. But a growing number of physicists are starting to whisper a different possibility. What if the anomalies are real? What if we've been wrong about the speed of light for a century? To understand why this matters so deeply, we need to start at the beginning. We need to meet the man who invented the rule everyone is now trying to break. The year was 1905. A 26-year-old patent clerk in Bern, Switzerland, sat at his desk, reviewing blueprints for electrical devices. His name was Albert Einstein. He was unknown to the scientific world. He had no laboratory, no research budget, no prestigious university position. And in that single year, he rewrote physics forever. Einstein was obsessed with a puzzle that had been driving scientists crazy for decades. Light behaved strangely. It did not follow the rules that governed everything else. If you throw a ball from a moving train, the ball picks up the train's speed. Simple, predictable. But light refused to play that game. Experiments had shown that light travelled at exactly the same speed, no matter how fast the source was moving. A beam of light from a stationary flashlight and a beam from a flashlight on a rocket moving at half the speed of light would both arrive at the same moment. This made no sense according to the physics of the time. Einstein did something bold. Instead of trying to explain why light broke the rules, he flipped the entire problem upside down. He declared that the speed of light was not a result of physics. It was a fundamental property of the universe itself, a constant, unchangeable, absolute. From this one assumption, everything else fell into place. Time slowed down for fast-moving objects. Space itself stretched and compressed. Mass and energy became two sides of the same coin, captured in the most famous equation ever written. Energy equals mass multiplied by the speed of light squared. Einstein's theory of special relativity was born. The consequences were staggering. A twin who travelled near the speed of light would return younger than the twin who stayed behind. A clock on a fast-moving spaceship would tick slower than a clock on Earth. Distances would shrink. Time would bend. Reality itself depended on how fast you were moving, and at the centre of it all stood the speed of light. Untouchable, unbreakable, the ultimate cosmic boundary. Einstein's theory predicted something darker too. As an object approached the speed of light, its mass would grow toward infinity. The energy required to push it any faster would also grow toward infinity. You could get close to the speed of light, but you could never reach it, never cross it. The universe itself would stop you. For decades, this was treated as settled science. Experiments piled up proving Einstein right. Atomic clocks on jets ticked slower than clocks on the ground. Particle accelerators showed particles gaining mass as they sped up. GPS satellites had to be adjusted for relativistic effects, or your phone would be off by miles every single day. Every prediction Einstein made held up under testing. The universe seemed to have a speed limit and nothing was allowed to cross it. But Einstein himself had a nagging worry. He once said the speed of light might not be as fundamental as he believed. He hinted in private letters that future discoveries could reveal deeper truths. He suspected the universe had secrets he had not yet uncovered. He died in 1955, leaving behind a completed picture of reality, or so everyone thought. Decades later, deep inside a mountain laboratory in Italy, a team of physicists was about to stumble into a measurement that would shake Einstein's locked universe to its core. Beneath the Gran Sasso mountain range in central Italy lies a laboratory buried under nearly a mile of solid rock. To reach it, you drive through a highway tunnel and turn off into a side passage that opens into an enormous underground cavern. The air is cold, the walls drip with moisture, and inside sit some of the most sensitive instruments ever built by humans. This is the Gran Sasso National Laboratory. It was constructed specifically to hide from the universe. The rock above blocks out cosmic rays and radiation from space, creating a quiet environment where researchers can detect the faintest of particles, the kind of particles that pass through entire planets without touching anything. In the year 2011, a team of physicists running an experiment called Opera made an announcement that sent shockwaves through the scientific world. They claimed to have measured particles travelling faster than light. The particles in question were neutrinos, ghostly bits of matter with almost no mass, capable of slipping through ordinary materials like a breeze passing through a window screen. Trillions of them pass through your body every second without you ever noticing. They come from the sun, from distant supernovae, from deep space. The Opera team had been firing neutrinos from CERN in Switzerland, a beam that travelled 450 miles through the Earth itself, arriving at the Gran Sasso detector in Italy. The experiment had been running for years. The data was carefully collected, and when researchers crunched the numbers, they found something impossible. The neutrinos were arriving at Gran Sasso about 60 billionths of a second earlier than light would have, a tiny fraction of a moment, but enough to shatter Einstein's speed limit. The announcement was made cautiously. The team did not claim to have broken physics. They presented their data and asked the global scientific community to help them figure out what was going on. Maybe there was an error they had missed. Maybe the equipment was flawed. Maybe the calculations had slipped somewhere. But if the data was correct, the implications were mind-bending. Newspapers around the world ran headlines announcing the death of Einstein's theory. Physicists on television debated whether reality itself needed to be rewritten. Time travel theorists celebrated. Students flooded their professors with questions. The scientific community split into camps. Some believed the measurement was real. Others insisted it had to be a mistake. The Opera researchers spent months checking every possible source of error. They examined the timing systems. They recalibrated the detectors. They reviewed the distance measurements down to the inch. They brought in outside experts to audit everything. Tension inside the Gran Sasso laboratory grew thick. Careers were on the line. Reputations hung in the balance. If the measurement turned out to be wrong, everyone involved would be associated with one of the most embarrassing mistakes in modern physics. If it turned out to be right, they would rewrite textbooks. Then, in early 2012, a technician noticed something strange about one of the fibre optic cables connecting the GPS timing system to the computer. It was loose, barely. A connection that should have been snug had developed a tiny gap over months of use. What they discovered next would become one of the most famous corrections in the history of science. The fibre optic cable was about as thick as a pencil. It connected the master clock to the computer that recorded when each neutrino arrived at the Gran Sasso detector. For years it had sat plugged into its port without anyone giving it a second thought. It was basic equipment, not glamorous, not exciting. Just a piece of infrastructure doing its job, except it had stopped doing its job properly. The gap at the connection was microscopic, too small to see with the naked eye, but it was enough to delay the timing signal by exactly the amount that had made the neutrinos appear to arrive 60 billionths of a second early. The math worked out perfectly. The anomaly was not a new law of physics, it was a flawed handshake between two pieces of electronics. When the cable was tightened and the experiment repeated, the neutrinos behaved exactly as Einstein predicted. They arrived right on schedule, not a nanosecond faster, not a nanosecond slower. The speed of light held firm. The scientific community breathed a collective sigh of relief. Einstein was safe. The universe still had its speed limit. reality still made sense. 3 senior members of the opera collaboration resigned from their leadership roles. The story became a cautionary tale taught in physics departments around the world. The message was clear: extraordinary claims require extraordinary evidence. And sometimes the most extraordinary-looking results turn out to be ordinary hardware failures. For most of the public, the story ended there. Einstein won. Neutrinos obeyed the rules. Move along, nothing to see. But something strange happened in the years that followed. Other experiments began producing other anomalies. Not the same kind, not as dramatic, but measurements that did not quite match what Einstein's theory predicted. Tiny discrepancies, fractions of fractions, results that hovered just on the edge of what could be explained away. At a laboratory in Illinois, researchers studying muons, which are heavier cousins of the electron, found the particles wobbling in a magnetic field at a rate that defied theoretical predictions. At facilities in Japan and Germany, neutrino experiments began detecting oddities in how particles shifted from one type to another. In quantum optics labs around the world, photons started doing things that seemed to violate locality, the principle that nothing can influence anything else faster than light. None of these anomalies were as dramatic as the Gran Sasso claim. None of them made front-page news. But together, they started to paint a picture that made physicists uneasy. Something was happening at the edges of measurement. Something small, something subtle, but consistent enough that it could not be dismissed. A new generation of experimentalists began asking a dangerous question. What if the Gran Sasso neutrinos were not the only time we thought light had been beaten? What if there were real anomalies, hidden under layers of experimental noise, that had been written off too quickly? The history of physics is full of revolutions that began with tiny, unexplained measurements. Planck discovered quantum mechanics by trying to explain a small mismatch in how hot objects glowed. Einstein himself built special relativity by taking seriously an experiment that most physicists had already dismissed. Now, a similar mood was creeping through the world's laboratories, and one experiment in particular was about to show results that were far harder to dismiss. In a quiet laboratory at Princeton University, a physicist named Lijun Wang was about to conduct an experiment that would confuse scientists for years. The year was 2000. Wang was not trying to break Einstein. He was trying to study how light behaves when it passes through unusual materials. His setup was elegant. A chamber filled with cesium gas. A laser firing pulses of light into the chamber. Detectors on both sides to measure when the light entered and when it exited. What Wang observed defied expectation. The light pulse appeared to leave the chamber before it finished entering. The peak of the outgoing pulse was detected 62 nanoseconds earlier than would have been possible if the light had travelled through the chamber at its normal speed. In fact, the pulse appeared to move at roughly 300 times the speed of light. News spread quickly. Had Wang discovered faster-than-light travel? The answer, it turned out, was complicated, and the reason why reveals something deep about how light actually behaves. A pulse of light is not a simple thing. It is made up of many different wavelengths bundled together. When this bundle passes through a special medium like cesium gas, the different wavelengths interfere with each other in peculiar ways. The peak of the pulse can appear to shift forward in time, making it seem like the pulse travelled faster than it should have. Think of it like a wave rolling onto a beach. The peak of the wave can crest and crash before the water behind it arrives. From a certain angle, it looks like the wave is moving faster than the water itself. But no individual water molecule is actually breaking any speed record. Wang's experiment was similar. The peak of the pulse appeared to move faster than light, but no single photon had actually crossed the speed limit. The information carried by the pulse, the actual signal, still obeyed Einstein's rules. This was the official explanation, and for many physicists it settled the matter, but a small number of researchers were not satisfied. They pointed out that the mathematics of Wang's experiment contained a subtle problem. The peak of the pulse did arrive early. That was a measured fact. The explanation that no information was transmitted depended on how you defined information. And some physicists began to wonder if the definition itself was a way of protecting Einstein's theory from inconvenient data. Other experiments followed. A team in Italy sent microwaves through a specially designed waveguide and reported similar effects. Researchers in Germany observed what they called superluminal tunneling, where photons appeared to leap across gaps faster than they should have been able to. In each case, the mainstream explanation was that the apparent faster-than-light behavior was an illusion of wave mechanics, not a real violation of Einstein's theory. But the measurements kept coming. Different labs, different setups, different teams, all finding the same strange effects. A pattern was forming. Under certain conditions, light appeared to cheat. It bent time. It slipped past barriers. It behaved as if the speed limit had cracks in it, even if those cracks could be explained away by clever mathematics. And then, in a laboratory in Italy, a pair of researchers set up an experiment so clean and so precise that the usual explanations would not work. The laboratory was in Turin, a city in northern Italy better known for its cars and its physics. But in a basement lab at the Politecnico di Torino, a small team of researchers was setting up an experiment so sensitive that it could measure the arrival of a single photon to within a fraction of a billionth of a second. Their setup was different from anything that had come before. They were not studying how light passed through special materials. They were studying how light behaved in free space, in the pure vacuum that fills the cosmos. The experiment involved shaping a laser pulse into an unusual geometric pattern. Most laser beams are simple, travelling in a straight line like a cone of light from a flashlight. But the Italian team twisted their beam into a structure that physicists call a Bessel pulse, a beam of light folded in on itself in a complex spiral. When they measured how fast this twisted beam travelled across their laboratory, the result was stunning. The beam arrived at its destination faster than light, and this time there was no cesium gas to blame, no waveguide to explain it away. The photons had travelled through plain, empty space, and they had gotten there ahead of schedule. The speed difference was tiny, a few parts per million, but it was measurable, it was repeatable, and it was happening in a setup where the usual excuses did not apply. The researchers published their findings carefully. They did not claim to have broken Einstein. They presented the data and offered several possible explanations, including the possibility that the unusual geometry of the beam was causing classical interference effects that made it look faster than it really was. But other physicists were less cautious. A few prominent theorists argued that the Italian experiment represented a genuine anomaly. Something was happening to the photons that could not be fully accounted for by standard physics. The beam was travelling faster than light, and no one could explain why. The debate erupted across physics journals and conference halls. Some researchers insisted the effect was real. Others argued it was an artifact of how the beam was shaped. Still others suggested that the geometry of the light itself might be somehow coupling to the structure of space-time in ways that classical theory could not describe. What made the Italian experiment so disturbing was its simplicity. This was not some exotic setup involving rare materials or extreme conditions. It was a laser, a vacuum, and a detector. The same kind of equipment used in laboratories around the world every day. If faster-than-light behavior could be observed in such a simple setup, how many other experiments had seen the same effect and dismissed it as noise? Researchers began going back through old data, papers from the 1990s, experiments from the early 2000s, measurements that had been filed away as anomalies and forgotten. And in several cases they found signals that looked suspiciously similar to what the Italian team had seen. A picture was emerging. The speed of light was not quite as constant as everyone had believed. Under certain conditions, involving certain geometries and certain setups, something strange was happening. Photons were slipping past the limit. The question was whether this was a real violation of Einstein's theory, or a hidden effect that could be explained within standard physics, and the next set of experiments would push the question even deeper. In a laboratory at the University of Geneva, Switzerland, a physicist named Nicholas Gisin was conducting experiments that would make the Italian results look almost ordinary. Gisin was studying something called quantum entanglement, the phenomenon that Einstein himself had once called spooky action at a distance. Entanglement is one of the strangest effects in all of physics. When two particles become entangled, they form a connection that transcends space. Measure one particle, and the other one instantly reflects the result, no matter how far apart they are. Gisin's team decided to test just how instant this connection really was. They created pairs of entangled photons in their laboratory and sent one of each pair to a village north of Geneva, while keeping the other one in a village to the south. The two villages were about 12 miles apart. Then they measured the photons. Every time they measured the photon in the northern village, the photon in the southern village matched the result instantly. Not almost instantly as far as the measurements could tell. Gisin's team went further. They calculated a lower bound for how fast the connection between the entangled particles would have to travel, if it was travelling at all. The answer was at least 10,000 times the speed of light, and that was just the minimum. The actual speed of the connection could be infinite. This was not a calculation error. It was not a loose cable. It was a repeatable, measurable effect that showed two particles communicating somehow across vast distances at speeds that made a mockery of Einstein's limit. But here is where things get even weirder. The standard explanation in quantum mechanics is that no information is actually being transmitted between the entangled particles. The connection is real, but it cannot be used to send a message. If you measure your particle in New York, the one in Tokyo instantly reflects the result, but you cannot control which result you get. Both observers see random patterns. Only when they later compare notes do the correlations become apparent. This is the escape hatch that saves Einstein's theory. Entanglement is real, but it does not violate the speed limit because no usable information is transmitted faster than light. Or so the textbooks say. In recent years, a handful of physicists have started questioning this interpretation. They point out that the correlations themselves are a form of information. Something is connecting the particles across space and time, and whatever that something is, it is operating faster than light. Experiments have been refined to test this more rigorously. In every test, entanglement behaves exactly as quantum mechanics predicts. The connection is instant. The correlations are perfect, and no matter how physicists try to design experiments that might show entanglement failing under certain conditions, it never fails. This is both reassuring and deeply unsettling. Reassuring because quantum mechanics works. unsettling because it works in ways that seem to openly defy the classical picture of space and time that Einstein gave us. Entanglement is real. Faster-than-light correlations are real. And no one truly understands how the universe pulls off this trick. The deeper physicists look into quantum entanglement, the stranger the results become, and the next set of experiments conducted deep in the vacuum of quantum tunneling would push the mystery even further. Imagine throwing a ball at a brick wall. In the ordinary world, the ball bounces back. The wall is solid. The ball does not have enough energy to break through. This is how everyday physics works. Now imagine that same ball is a quantum particle. And imagine the wall is a barrier made of energy rather than bricks. What happens is one of the most bizarre effects in all of nature. The particle sometimes appears on the other side of the wall, as if it had passed through without ever physically crossing the space in between. Physicists call this quantum tunneling. And it happens all the time in the real world. It is how the sun generates energy, with protons tunneling through barriers inside its core. It is how certain electronic components work, with electrons slipping through insulators they should not be able to cross. It is fundamental to the chemistry of life itself. For decades, physicists assumed that tunneling, while strange, still obeyed the speed of light. A particle might cheat its way through a barrier, but the time it took to do so should be bounded by Einstein's rule. Experiments in the 1990s began suggesting otherwise. A team led by Raymond Chiao at the University of California, Berkeley measured how long it took photons to tunnel through a specially designed optical barrier. The barrier was thin, only a fraction of a millimeter thick. According to classical expectations, the photons should have crossed it in a predictable amount of time. Instead, they crossed it in almost no time at all. The measured tunneling speed was roughly 1.7 times the speed of light. Not a subtle anomaly, not a fraction of a percent, a massive, undeniable violation of the expected behavior. Chiao published his results and braced for backlash. It came. Other physicists argued that the apparent superluminal speed was another illusion of wave mechanics. The peak of the pulse appeared to shift forward, just like in Wang's experiment with cesium gas, but no real information had been transmitted faster than light. Chiao disagreed. He pointed out that his experiments were more carefully designed than earlier ones, and that the usual explanations did not fully account for his results. Other teams repeated the experiment with different setups. A group in Germany led by Günther Nimtz used microwaves to tunnel through a waveguide barrier and reported speeds up to 5 times the speed of light. A Japanese team found similar effects with infrared pulses. Every experiment produced the same basic result. Particles tunneling through barriers moved faster than light. The debate grew heated. Nimtz was so convinced that tunneling violated Einstein's rule that he encoded Mozart's 40th Symphony onto a microwave pulse and transmitted it through a waveguide at superluminal speed. The signal came out the other side recognizable faster than it should have. Critics insisted the effect was still an illusion. The envelope of the pulse moved faster than light, but the leading edge did not. No real information was transmitted superluminally, they argued. Nimtz responded that Mozart was being transmitted, Mozart was information, and therefore Einstein was being broken. The argument has never been fully resolved. Quantum tunneling remains one of the most debated phenomena in physics. Some researchers see it as a genuine crack in relativity. Others see it as a subtle wave effect that leaves Einstein intact. But the anomalies were not confined to light. Other particles were behaving strangely too. And the next experiment involved particles so mysterious that scientists still do not fully understand them. Deep in the flat cornfields of Illinois sits a circular structure about 50 feet across. From above, it looks like a giant metal donut. It is one of the most precise instruments ever built for measuring the behavior of subatomic particles. Inside its ring, particles called muons race around at nearly the speed of light, wobbling in a powerful magnetic field. The instrument is called Muon G-2. It operates at Fermilab, one of America's premier physics laboratories, and in the year 2021, it announced a result that stunned the scientific community. The muons were wobbling wrong. Muons are essentially heavy versions of electrons. They are fundamental particles that carry a small magnetic moment, which means they act like tiny bar magnets. When you place a muon in a magnetic field, it wobbles at a specific frequency, much like a spinning top. The exact frequency of this wobble is predicted by something called the Standard Model of particle physics. The Standard Model is one of the most successful scientific theories ever created. It describes every known particle and force in the universe except gravity. It has been tested thousands of times and confirmed to astonishing precision. If the Standard Model predicts a number, experiments almost always match it, except for the muon wobble. When the Fermilab team measured how fast the muons were wobbling, the result was slightly off from what the Standard Model predicted. Not by much, a difference of about 2.5 parts per million. But in the world of precision physics, that is a massive discrepancy. The team had not expected to find this. They had run their experiment expecting to confirm the Standard Model prediction. Instead, they found a gap. A tiny, stubborn gap that refused to go away no matter how many times they rechecked their data. The implications were enormous. If the muon was wobbling at an unexpected rate, it meant some unknown particle or force was influencing it. Something not included in the Standard Model. Something hiding in the quantum fabric of space itself. Speculation ran wild. Some theorists suggested new heavy particles that physicists had not yet discovered. Others proposed new forces that operate only at incredibly short distances. A few even suggested that the discrepancy might hint at a breakdown in relativity itself, a tiny deviation from Einstein's rules that had been hiding in the muon data for decades. The story got more complicated. A separate calculation of the Standard Model prediction, done by a different group using a newer technique called lattice quantum chromodynamics, produced a number that actually matched the Fermilab measurement. This raised the possibility that there was no anomaly at all, just a disagreement about the theoretical prediction. Physicists split into camps. One camp insisted the anomaly was real and pointed to new physics. Another camp argued the theoretical calculation needed to be refined before any conclusions could be drawn. As of the most recent measurements, the debate remains unresolved. The muons continue to wobble at their mysterious rate. The theorists continue to argue about what the correct prediction should be, and physicists everywhere watch Fermilab for the next round of data. What is certain is this: somewhere in the behavior of muons, the universe is hiding a secret. A secret that might, just might, connect to the other speed-of-light anomalies that have been popping up in laboratories around the world. In a cavern buried 2 miles beneath the surface of Sudbury, Ontario, sits a massive spherical tank filled with heavy water. The sphere is about 40 feet across, lined with photomultiplier tubes that watch for the faintest flickers of light. This is the Sudbury Neutrino Observatory, and in the year 2001, it solved one of the most stubborn mysteries in physics. The mystery was about the sun. For decades, scientists had calculated how many neutrinos the sun should be producing through the nuclear reactions in its core. They then built detectors on Earth to catch these neutrinos and confirm the calculation. The detectors caught far fewer neutrinos than predicted, about a third of the expected amount. The gap was huge and persistent. Every experiment for 30 years found the same shortfall. Either the sun was not working the way physicists thought, or the neutrinos were doing something weird between the sun and Earth. The Sudbury Observatory was built specifically to solve this puzzle, and when the data came in, the answer was stunning. Neutrinos were changing their identity mid-flight. In the standard model, there are 3 types of neutrinos: electron neutrinos, muon neutrinos, and tau neutrinos. For a long time, physicists assumed these 3 types were distinct. A neutrino born as an electron neutrino stayed an electron neutrino forever. The Sudbury team showed this was wrong. Neutrinos oscillate. They shift from one type to another as they travel through space. The neutrinos produced in the Sun were mostly electron neutrinos, but by the time they reached Earth, many had transformed into muon or tau neutrinos. Since the old detectors could only see electron neutrinos, they missed 2/3 of what was actually arriving. This discovery won a Nobel Prize, but it opened a new can of worms. For neutrinos to oscillate, they must have mass. This contradicted the standard model, which originally assumed neutrinos were massless. If neutrinos have mass, even a tiny amount, they cannot travel at exactly the speed of light. They should be slower, measurably slower. But here is the twist. When physicists measured neutrinos from a supernova in 1987, the neutrinos arrived at Earth just a few hours before the light from the explosion. Across a distance of about 170,000 light-years, meaning the neutrinos had travelled at almost exactly the speed of light, despite having mass. The numbers suggested something strange. The neutrinos were either travelling at the speed of light, which should be impossible for massive particles, or travelling extremely close to it. Physicists accepted the second explanation. Neutrinos are so light that their speed is indistinguishable from light speed in practice. But a few theorists noticed something troubling. The calculations required neutrino masses to be incredibly, almost impossibly small, about 1,000,000 times lighter than the electrons. And nobody knew why. The standard model offered no explanation for why neutrinos should have such tiny masses. Some physicists began to wonder if something else was going on. Were neutrinos really massive particles that happened to travel near light speed? Or were they something stranger, some kind of particle that skirted the edges of relativity in ways that had not yet been understood? New experiments were being designed to measure neutrino behavior with greater precision than ever before, and what they found would suggest that the ghostly particles were hiding even more secrets than anyone had imagined. At a nuclear reactor in southern China, a team of physicists from across the world set up an experiment in the early 2010s to count antineutrinos. These are the antimatter cousins of neutrinos, produced in huge numbers by the reactions inside nuclear power plants. The experiment was called Daya Bay, and it was designed to answer a specific question. How exactly do neutrinos change from one type to another as they travel? The team set up detectors at various distances from the reactors, some close, some far. By comparing the number of antineutrinos detected at different distances, they could calculate how often the particles were oscillating between types. The results were precise. The researchers confirmed that antineutrinos, like neutrinos, do indeed oscillate. They mapped out the exact pattern of how the oscillations happened. They won major awards for their work. But there was a problem, a shadow that lurked at the edges of their measurements. The total number of antineutrinos coming out of the reactors was slightly lower than expected. about 6% lower. 6% might not sound like much, but in particle physics it is a mountain, and this anomaly, which became known as the reactor antineutrino anomaly, could not be easily explained. One possibility was that the theoretical predictions of how many antineutrinos the reactors should produce were wrong. Maybe the nuclear reactions inside the reactor cores were being miscalculated. Another possibility was far more exotic. What if the antineutrinos were oscillating into a new, unknown type of particle? Physicists called this hypothetical particle the sterile neutrino. It would be a fourth kind of neutrino, one that did not interact with ordinary matter in any detectable way. If sterile neutrinos existed, they would be truly bizarre. They could only be detected indirectly, by the amount of other neutrinos they stole away through oscillation. They might have masses very different from the three known neutrino types. And most disturbingly, they might not be bound by the same rules that governed ordinary particles. Some theorists speculated that sterile neutrinos could travel faster than light. Not through ordinary space, but through hidden dimensions that physicists had long theorized might exist. If true, the 6% missing antineutrinos at Daya Bay could be evidence that particles were slipping into these dimensions and re-emerging in ways that violated standard speed limits. The idea was controversial. Most physicists remained skeptical. Sterile neutrinos were an elegant theoretical possibility, but solid experimental evidence was lacking. Then, over the following decade, more experiments began reporting anomalies. A detector in New Mexico called LSND found excess signals that could be explained by sterile neutrinos. A follow-up experiment at Fermilab called Mini Boon found similar anomalies. A Russian experiment called BEST, using radioactive gallium, found results consistent with sterile neutrinos as well. Each individual anomaly could be explained by measurement error or theoretical uncertainty. But together, they formed a pattern. Something was going on in the neutrino sector that the standard model could not easily account for. In 2022, a new experiment called Stereo, operating at a reactor in France, reported results that seemed to rule out certain sterile neutrino scenarios. But it did not close the door entirely. The anomalies persisted at lower levels, still tantalizing, still unexplained. Physicists found themselves in a strange position. They would not confirm the existence of sterile neutrinos, but they could not rule them out either. The particles remained in a quantum limbo, possibly real, possibly imaginary, possibly something stranger than either. If sterile neutrinos really do exist, and if they really do travel faster than light by slipping through hidden dimensions, then the universe is far stranger than it appears. To understand why, we need to take a brief detour into some of the wildest ideas in modern theoretical physics. For most of the 20th century, physicists assumed the universe had exactly 3 dimensions of space and 1 of time: up, down, left, right, forward, backward, and the flow of time. That was it. 4 dimensions total, nice and tidy. Then came string theory. String theory emerged in the 1970s as an attempt to unify quantum mechanics with gravity. The mathematics of the theory demanded extra dimensions, not just 4, not just 5, 10 or 11 dimensions depending on which version you asked about. Where were these extra dimensions hiding? According to string theorists, they were curled up so small that they were invisible to ordinary instruments. Picture a long garden hose seen from a great distance. It looks like a line, a one-dimensional object, but up close, you see that the hose is actually a tube, with another dimension wrapped around its length. Extra dimensions in physics could work the same way. Present everywhere, but coiled up at scales far smaller than any atom. For decades, string theory lived in the realm of pure mathematics, beautiful equations that predicted a universe more complex than anything Einstein had imagined, but with no experimental evidence. Critics called it untestable. Supporters called it the only game in town. Then physicists began asking a provocative question. What if particles could leak into these hidden dimensions? What if certain particles, under certain conditions, could take shortcuts through the extra dimensions that made them appear to travel faster than light in our ordinary three-dimensional space? The mathematics worked out. A particle that could enter a hidden dimension could theoretically traverse a distance that looked enormous in our world, but was short in the extra dimension. Emerging at the other end, the particle would appear to have moved faster than light, even though it had never actually violated Einstein's rules within any single dimension. This is sometimes called the shortcut hypothesis, and some theorists believe it might explain the neutrino anomalies. If certain neutrinos can briefly enter a hidden dimension, they could effectively teleport across vast distances. They would appear to arrive at detectors earlier than light. They would seem to oscillate in ways that standard four-dimensional physics could not predict. The missing anti-neutrinos at Daya Bay could be particles that had taken a detour through the fifth dimension and not come back. The idea sounds like science fiction, and many mainstream physicists treat it that way. But a growing number of researchers have begun taking it seriously. Experiments are being designed to look for specific signatures of dimensional shortcuts. Detectors are being upgraded to catch particles behaving in ways that only extra dimensions could explain. So far, no direct evidence of hidden dimensions has been found. The extra dimensions, if they exist, are proving extremely shy about revealing themselves. But the faster-than-light anomalies keep appearing. In neutrinos, in photons, in quantum tunneling experiments, and every time one of these anomalies pops up, the shortcut hypothesis gets a little harder to dismiss. If the universe really does have extra dimensions, then the speed of light is not the ultimate barrier it appears to be. It is merely the speed limit for particles stuck in our four-dimensional slice of a much larger reality. And some particles, it seems, might know how to escape. About 55 million light-years from Earth, at the centre of the galaxy M87, sits a black hole so massive that it bends space into impossible shapes. Its mass is roughly 6.5 billion times that of our Sun. In 2019, an international team of astronomers released the first ever direct image of this black hole, a ghostly orange ring surrounding a pitch-black void. The image was a triumph of modern science. It confirmed Einstein's theory of general relativity with extraordinary precision. The shadow of the black hole had exactly the shape and size that the theory predicted, and yet, buried in the details of the image, there were hints of something strange. Black holes are the ultimate test of Einstein's theory. They are regions where the gravity is so intense that not even light can escape. The boundary around a black hole, called the event horizon, is supposed to be the ultimate speed of light barrier. Inside it, nothing can outrun the pull of gravity, no matter how fast. But what happens at the event horizon itself? The mathematics of general relativity breaks down there. Equations that work everywhere else in the universe produce impossible answers at the edge of a black hole. Quantities that should be finite become infinite. Time itself seems to stop. For most of the 20th century, physicists treated this as a mathematical quirk. The equations failed at the horizon, but the physical reality was assumed to be well behaved. Nothing particularly weird was thought to happen at the edge of a black hole. An astronaut falling in would notice no special boundary. She would simply cross the horizon, and continue falling toward the centre. Then Stephen Hawking came along. In 1974, Hawking made a discovery that changed everything. He showed that black holes are not perfectly black. They emit a faint glow of particles called Hawking radiation, due to quantum effects at the event horizon. Over incredibly long timescales, this radiation causes black holes to slowly evaporate. Hawking radiation created a paradox that physicists are still struggling to solve. If a black hole evaporates, what happens to the information about everything that fell into it? According to quantum mechanics, information cannot be destroyed. But Hawking's calculations suggested that the radiation carried no information about what had gone into the hole. The information seemed to simply vanish. This is the black hole information paradox, and resolving it may require rewriting either quantum mechanics or general relativity. Possibly both. Some theorists believe the paradox points to faster-than-light effects. If information about objects falling into a black hole is somehow preserved in the outgoing Hawking radiation, then the information must be transmitted from deep inside the event horizon to the outside, which would mean something is moving faster than light across the boundary. Other physicists have proposed that black holes are surrounded by firewalls, a boundary layer of high-energy particles that could destroy any information falling in. Still others suggest that the interior of a black hole connects to other universes through wormholes, creating shortcuts through space-time that could transmit information at effectively infinite speeds. None of these ideas have been confirmed, but all of them point in the same direction. The inside of a black hole is a place where the rules we know do not fully apply. The speed of light, so rigid elsewhere in the universe, may not hold its grip at the most extreme boundaries of reality. And the strangeness is not confined to black holes. Here is something that might blow your mind. Every night when you look up at the sky, you are seeing galaxies that are moving away from Earth faster than the speed of light. This sounds impossible. Einstein said nothing can travel faster than light. So how can entire galaxies be doing it? The answer lies in a subtle distinction that most people have never heard of. Einstein's speed limit applies to motion through space. Nothing within space can exceed the speed of light. But space itself is not bound by this rule. Space can stretch, space can expand, and the expansion of space can carry distant objects away from us faster than any particle could ever travel. The universe has been expanding since the Big Bang, about 13.8 billion years ago. In the distant past, all matter was compressed into an incredibly dense, hot state. Then something caused it to explode outward. Not an explosion into empty space, but an explosion of space itself. Space has been growing larger ever since. In the 1990s, astronomers made a stunning discovery. The expansion of the universe is not slowing down, as everyone had expected. It is speeding up. Some mysterious force, which physicists call dark energy, is pushing the universe apart faster and faster. As the universe expands, the distances between galaxies grow. For nearby galaxies, this growth is small, and the galaxies appear to move away slowly. But for galaxies that are far away, the accumulated expansion adds up to tremendous speeds. At a certain distance, called the Hubble horizon, the expansion of space carries galaxies away from us at exactly the speed of light. Beyond that distance, galaxies recede faster than light. There are galaxies in the observable universe right now that are receding from Earth at several times the speed of light. Light from these galaxies that was emitted long ago is still reaching us, because it was heading our way before the expansion got out of hand. But any light they emit today will never reach us. Ever. They are forever beyond our reach, even though we can still see them as they looked in the past. This raises a profound question. If space can expand faster than light, what exactly is space? Is it a medium, a fabric, a field? Physicists do not fully know. General relativity treats space as a geometric backdrop, a stage on which matter and energy play out. But the fact that this backdrop can stretch faster than any particle suggests that space might be something more substantial than an empty backdrop. Some theorists have proposed that space is filled with a kind of quantum foam, a bubbling sea of virtual particles constantly popping in and out of existence. Others suggest that space has hidden properties we have not yet detected, properties that might allow certain types of signals or influences to spread through it at speeds beyond Einstein's limit. The dark energy that is driving the accelerating expansion is itself a mystery. No one knows what it is. It makes up about 68% of the total energy in the universe, yet it has never been directly detected in any laboratory. Something is pushing space apart, and we do not know what. The universe, it seems, is full of loopholes in Einstein's rules. Expanding space sidesteps the speed limit. Black holes challenge the mathematics. And at the smallest scales, in the quantum realm, reality gets even stranger. Most people have heard of quantum mechanics. Fewer people know that there are several competing interpretations of what quantum mechanics actually means. The math is the same in every interpretation. The predictions are the same. But the underlying picture of reality is radically different. The most famous interpretation is the Copenhagen interpretation, developed in the 1920s by physicists like Niels Bohr and Werner Heisenberg. In this view, particles do not have definite properties until they are measured. Before measurement, a particle exists in a cloudy state of possibilities. Measurement collapses the cloud into a single outcome, seemingly at random. This interpretation works. It predicts experimental results with stunning accuracy, but it leaves many people deeply unsatisfied. What does it mean for a particle to not exist until it is observed? Why would the universe be so strange? In 1927, a French physicist named Louis de Broglie proposed a different interpretation. In his view, particles do have definite properties at all times. They are also guided by invisible waves, which he called pilot waves. The wave tells the particle where to go. The randomness we observe in quantum experiments comes from our inability to see the pilot wave directly. De Broglie's idea was largely forgotten until an American physicist named David Bohm revived it in the 1950s. Bohm developed the pilot wave theory into a fully worked out alternative to the Copenhagen interpretation. In his version, the universe is completely deterministic. Everything is predetermined by the pilot waves guiding every particle in existence. But Bohm's theory had a disturbing feature. The pilot waves had to be able to transmit influences faster than light, much faster, essentially instantaneous, across any distance. Think about it this way. If two particles become entangled and one of them is measured, the pilot wave must instantly adjust to reflect the result. If the two particles are light years apart, the pilot wave has to communicate across those light years in an instant. Einstein's speed limit does not apply to the pilot wave, because the wave is not a physical object moving through space. It is something more fundamental, some kind of background field that carries influences at infinite speed. For most physicists, this was a deal-breaker. Faster-than-light effects violated Einstein's theory, and nobody wanted to go there. Pilot wave theory was shelved. The Copenhagen interpretation remained dominant. In recent decades, pilot wave theory has been quietly making a comeback. Experiments have shown that certain classical systems, involving droplets of silicon oil bouncing on a vibrating surface, exhibit behavior remarkably similar to quantum pilot waves. The droplets are guided by waves on the surface of the oil, and they reproduce many of the famous quantum effects, including interference patterns that were long thought to be purely quantum. These experiments do not prove that pilot wave theory is correct, but they show that the idea is not as crazy as it once seemed. Reality might be guided by waves we cannot directly see, and those waves might operate at speeds far beyond light. If pilot wave theory is right, then the universe is full of faster-than-light signals, not transmitting information we can use, but orchestrating the behavior of every particle in every corner of space. A cosmic symphony conducted by invisible waves traveling at unlimited speed. It is a beautiful idea, and it might be closer to the truth than we realize. Deep in the quantum world, something happens that seems to violate one of our most basic intuitions about time. A measurement made in the present can affect events in the past, not metaphorically, actually affect them. This phenomenon is called retrocausality, and it has been demonstrated in experiments that still leave physicists scratching their heads. The most famous version is called the delayed choice experiment. It was first proposed by the American physicist John Wheeler in the 1970s. The setup is simple in principle, though tricky in practice. Imagine a photon travelling through an apparatus that can either be configured to reveal the photon's wave nature or its particle nature. You decide which configuration to use after the photon has already entered the apparatus. Somehow, the photon adjusts its behavior to match your choice, even though the choice was made after the photon had already committed to either wave-like or particle-like travel. Experiments confirm this. The photon behaves as a wave when you measure it as a wave. It behaves as a particle when you measure it as a particle. The timing of your measurement, made after the photon has already travelled through the apparatus, determines the photon's earlier behavior. This is not supposed to be possible. In classical physics, the past is fixed. You cannot change what happened yesterday, but in the quantum realm, the past seems to remain flexible until it is locked in by measurement. Physicists have been arguing about what this means for decades. Some argue that retrocausality is real. Information from the future travels backward to influence the past. Others insist this is a misinterpretation of the math. The photon does not retroactively change. Rather, our description of its behavior is necessarily entangled across time in ways that look like retrocausality, but are actually something subtler. Either way, the experiments keep showing the same thing. Quantum systems do not respect the tidy separation between past and future that we experience in everyday life. Time, in the quantum world, flows both ways. Recent experiments have pushed retrocausality even further. A team in Israel performed a version of the delayed choice experiment using entangled photons. They were able to measure a photon after its entangled partner had already been destroyed. The results suggested that the measurement still affected the destroyed partner, even though it no longer existed. Let this sink in for a moment. Actually, strike that phrase. What these experiments suggest is that the universe does not work the way our intuitions tell us it should. Cause and effect, past and future, before and after. These concepts may be approximations that hold in everyday life but break down at the deepest levels of reality. If retrocausality is real, then information can travel backward in time, which means, in a sense, faster than light. Light moves forward in time at a fixed speed. Information travelling backward through time effectively arrives before it was sent. It reaches its destination before the signal was even created. This is deeply unsettling. It violates our basic understanding of what is possible. It also matches suspiciously with the other anomalies we have been examining. Entanglement correlations that defy distance, tunneling particles that outrun light, neutrinos that may skirt hidden dimensions, retrocausal effects that fold time back on itself. The universe, it seems, has many ways of circumventing Einstein's speed limit. Some known, some suspected, some still hidden in the darkness of experiments yet to be performed. The empty space between stars, the void between atoms, even the emptiness inside your own body. These are not truly empty. Modern physics has discovered that what we call vacuum is actually seething with activity at the smallest scales, and that activity may hold clues to how the speed of light itself is determined. In the quantum picture of reality, particles constantly pop into and out of existence in empty space. These are called virtual particles. They appear for tiny fractions of a second, then vanish. They cannot be directly observed, but their effects can be measured. One of the most striking demonstrations of this is the Casimir effect, predicted in 1948 by a Dutch physicist named Hendrik Casimir. He showed that two flat metal plates placed very close together in a vacuum would feel an attractive force pulling them toward each other. The force comes from the fact that the space between the plates contains fewer virtual particles than the space outside them. The difference creates a pressure that pushes the plates together. The Casimir effect has been measured directly in laboratories around the world. It is real. Empty space really does contain a froth of virtual particles that exert measurable forces on matter. Here is where things get interesting for our investigation of the speed of light. The speed of light in vacuum is determined by two fundamental constants of physics: the electric permittivity of space and the magnetic permeability of space. These constants describe how easily electric and magnetic fields propagate through the vacuum, and they are set, in part, by the sea of virtual particles in empty space. If the density of virtual particles changes, the speed of light might change too. In 2016, a team of physicists at the University of Lyon in France made a startling prediction. They calculated that when light passes through a region with a slightly different vacuum structure, such as between the plates of a Casimir experiment, the speed of light should be subtly altered. The effect would be tiny, a fraction of a part in a trillion, but measurable in principle. If their prediction is correct, then the speed of light is not a universal constant after all. It depends on the local structure of the vacuum. In regions where the quantum foam is denser or sparser than average, light could travel slightly faster or slower. This idea is still controversial. No experiment has yet confirmed the effect, but it raises a profound possibility. The speed of light might be a local property of our particular region of the universe, shaped by the vacuum conditions around us. In distant parts of the universe, where the vacuum structure might be slightly different, light might travel at slightly different speeds. Across cosmic distances, these differences could add up. Light from distant galaxies might not be arriving at us at the speed we assume. Some astrophysicists have been looking for exactly this kind of effect. They compare light from extremely distant sources at different wavelengths, checking whether different colours arrive at slightly different times. So far, the results are inconclusive, but the search continues. If the speed of light varies across space, then our entire picture of the universe would need to be revised. Distances, ages, expansion rates. All would depend on assumptions about a constant speed of light that might not be quite as constant as Einstein believed. The vacuum, it turns out, might be one of the strangest things in the universe. And the next anomaly we will examine involves a measurement that seems to reach beyond it. hidden inside the equations of physics is a number so important that some scientists have called it the magic number at the heart of the universe. It is called the fine structure constant. Its value is approximately 1/137. This number controls how strongly electrons interact with light. It determines the colours of atoms, the stability of matter, the chemistry of life. If the fine structure constant were even slightly different, the universe would be a radically different place. Stars would not shine the way they do. Atoms would not hold together. You would not exist. For most of the 20th century, physicists assumed this constant was truly constant, a fixed number, the same everywhere in the universe, the same yesterday and tomorrow. Then astronomers started looking at very distant quasars, bright objects powered by supermassive black holes billions of light years away. By analysing the light from these quasars, researchers could measure what the fine structure constant was in the early universe, because that light had been travelling for billions of years before reaching Earth. The results were strange. An Australian astrophysicist named John Webb led a team that studied hundreds of quasars and found that the fine structure constant seemed to vary across the sky. In one direction, it appeared slightly smaller than its value on Earth. In the opposite direction, it appeared slightly larger. The variation was tiny, only a few parts per million, but it was consistent across many observations. If Webb's team was right, then one of the fundamental constants of physics is not actually constant. It changes depending on where you look in the universe. This has huge implications for the speed of light. The fine structure constant is mathematically tied to the speed of light. If the fine structure constant varies, then either the speed of light varies, or one of the other constants in the equation does. Neither option fits comfortably with standard physics. Other teams rushed to check Webb's findings. A group using the Very Large Telescope in Chile found similar variations. A team using the Keck Observatory in Hawaii found them too. But a different group, analysing a separate data set, reported no significant variation. The debaters raged for years. Some physicists argue that Webb's results are real evidence of varying constants. Others argue they are artifacts of the way the data was analysed or collected. The measurements are near the limits of what current telescopes can do, and the variations, if real, are tiny. In 2020, a team reported new measurements from a quasar 12 billion light-years away, using improved techniques. They found hints of variation, but not enough to settle the debate. The stakes are enormous. If the fine structure constant really does vary, then the universe is not as uniform as cosmologists have long assumed. Different regions of space may have slightly different physical laws. The speed of light might itself be a local quantity, not a universal one. Some theorists have developed models where the fine structure constant changes over time, driven by yet another hypothetical field that pervades the universe. These models predict specific patterns of variation that future observations could confirm or rule out. For now, the question remains open. The magic number at the heart of physics might be slowly drifting, and if it is, our entire picture of the cosmos may need revision. In 1972, NASA launched a small spacecraft named Pioneer 10. A year later, its twin, Pioneer 11, followed it into the solar system. These were the first human-made objects designed to travel beyond the orbit of Pluto and into interstellar space. They carried cameras, instruments, and a small plaque with a message for any aliens who might someday find them. For decades, the Pioneer probes performed flawlessly. They sent back data from Jupiter and Saturn. They provided the first close-up images of the outer planets. They continued transmitting as they raced outward toward the stars. Then something strange started happening. As the probes moved farther from the sun, they began slowing down slightly more than they should have been. According to standard physics, their trajectories should have been determined entirely by the gravity of the sun and the planets. Nothing should have been pulling them back or slowing them down, but something was. The effect was tiny. The probes were decelerating at a rate of about 8 parts per 10 billion of standard gravity, so small that it took years of careful tracking to notice, so subtle that at first scientists assumed it was a calculation error. But the effect was there. Both Pioneer 10 and Pioneer 11 were experiencing the same anomalous deceleration. The numbers matched between the two probes. Something was happening to them that was not predicted by known physics. Theories multiplied. Maybe there was extra gas in the outer solar system slowing down the probes. Maybe the probes were leaking fuel in a way that produced a small thrust. Maybe the heat emitted by the probes themselves was pushing them slightly off course. Each theory had problems. The outer solar system is extremely empty, and not enough gas exists to slow down a spacecraft by the observed amount. The probes did not seem to be leaking fuel in any detectable way. Thermal effects from the onboard nuclear generators could contribute, but it was difficult to see how they could produce the exact deceleration observed. Some theorists went bolder. They suggested that the Pioneer anomaly might be evidence that gravity itself behaves differently at the edges of the solar system. If gravity gets slightly stronger far from the sun, the probes would decelerate exactly as observed. This would contradict Einstein's theory of general relativity, which predicts that gravity weakens with distance in a specific, well-understood way. A few physicists even suggested that the anomaly might be linked to the speed of light. If light from distant sources travels slightly slower due to some unknown effect in the vacuum, then calculations of spacecraft positions based on light signals could be systematically off. The Pioneer anomaly might not be a real force on the probes, but a subtle mismatch between the actual and assumed speed of light. After years of analysis, a team led by physicist Slava Turishev concluded in 2012 that the Pioneer anomaly was almost entirely explained by thermal radiation from the probes themselves. Heat from the nuclear generators was being emitted in a slightly asymmetric pattern, producing a tiny thrust that pushed the probes back toward the sun. The official explanation satisfied most physicists, but a few remained unconvinced. They argued that the thermal model relied on assumptions about heat distribution that could not be directly verified, and they pointed out that similar anomalies had been hinted at in other spacecraft tracking data. The Pioneer anomaly faded from the headlines. But it left a lingering question. How much of what we think we know about gravity and light is based on assumptions we have not fully tested? Another strange spacecraft mystery has puzzled scientists for over 2 decades. It is called the flyby anomaly. And unlike the Pioneer anomaly, no one has a convincing explanation for it. When spacecraft travel through the solar system, they often use the gravity of Earth to boost their speed. This is called a gravity assist. The spacecraft swoops close to Earth, borrows some of our planet's orbital momentum, and flies away faster than it arrived. It is a standard technique, used for decades to send probes to the outer planets. In 1990, NASA's Galileo spacecraft performed a flyby of Earth on its way to Jupiter. When engineers tracked the spacecraft's speed after the flyby, they noticed something odd. Galileo was moving faster than calculations predicted. Not by much, about 3 millimeters per second faster, but measurable. A small error, they thought. Probably a rounding issue somewhere in the tracking software. Then the Near-Earth Asteroid Rendezvous spacecraft performed a flyby in 1998. Same effect. It gained a small amount of extra speed that should not have been there. Then came Cassini in 1999. Same effect. Then Rosetta in 2005. Same effect again. Different spacecraft, different trajectories, different tracking stations, all gaining small amounts of unexplained extra speed during Earth flybys. The pattern was consistent but weird. Some flybys showed large anomalies, up to 13 millimeters per second. Others showed tiny ones. A few showed no anomaly at all. Physicists struggled to find any parameter that correlated cleanly with the size of the effect. Researchers tried every conventional explanation. Maybe Earth's atmosphere was causing extra drag. Maybe Earth's gravitational field was slightly non-uniform in ways that affected the flybys. Maybe solar radiation pressure was pushing the spacecraft in unexpected directions. None of these explanations worked. The atmospheric drag would be too small. The gravitational variations would be too uniform. Solar radiation would affect all flybys similarly. Some theorists began proposing exotic explanations. Maybe dark matter, the mysterious substance that makes up most of the universe's mass, was concentrated around Earth in ways that affected spacecraft. Maybe Earth was generating subtle gravitational fields that standard relativity could not account for. A few even suggested that the anomaly might be linked to variations in the speed of light near Earth. If light behaves slightly differently in Earth's gravitational well, then radio tracking signals could produce systematic errors that looked like extra speed. In 2008, a physicist named John Anderson published a paper suggesting that the flyby anomaly might be related to Earth's rotation. He proposed an empirical formula that predicted the anomaly based on the angles at which spacecraft approached and departed from Earth. The formula fit the data surprisingly well, but the formula had no theoretical foundation. It described what was happening without explaining why. Anderson himself acknowledged that a deeper physical mechanism was needed. The flyby anomaly has largely faded from public attention. NASA has continued to perform flybys, and more recent ones have shown smaller or no anomalies. Some researchers believe the effect was an artifact of imperfect tracking methods that have since been improved. Others believe it was real and points to unknown physics. Either way, the anomaly represents something unsettling. Even in our own backyard in the well-studied space around Earth, there are measurements that standard physics cannot fully account for, and these measurements involve tracking signals that travel at the speed of light. Let us return to neutrinos, because they keep throwing up surprises, and because one of their deepest mysteries may connect directly to the speed of light. Every fundamental particle has an antimatter partner. Electrons have positrons. Protons have antiprotons. Quarks have antiquarks. When a particle meets its antiparticle, they annihilate each other, converting their mass entirely into energy. But neutrinos are peculiar. No one knows for certain whether they have distinct antiparticles or whether they are their own antiparticles. A particle that is its own antiparticle is called a Majorana fermion, named after the Italian physicist Ettore Majorana, who first proposed the idea in 1937. Majorana himself was a fascinating figure, brilliant, reclusive, and deeply troubled. In 1938, he vanished without a trace during a boat trip, leaving behind only cryptic notes. His disappearance has never been solved. His mathematical legacy, however, continues to shape physics. If neutrinos are Majorana particles, they would be unlike any other matter we know. They would blur the line between particle and antiparticle, existing in a strange middle ground, and they would open the door to processes that otherwise could not occur. One such process is called neutrinoless double beta decay. In ordinary double beta decay, two neutrons in an atomic nucleus convert into two protons, emitting two electrons and two antineutrinos. But if neutrinos are their own antiparticles, the two antineutrinos could annihilate each other inside the nucleus, leaving only two electrons emerging. Experiments around the world are hunting for this rare process. Deep underground detectors in Italy, Japan, Canada, and the United States are watching for the telltale signal of neutrinoless double beta decay. If it is observed, it would confirm that neutrinos are Majorana particles. It would explain why matter dominates over antimatter in the universe, one of the great unsolved mysteries of cosmology. And it might connect to the speed of light in unexpected ways. Majorana neutrinos are predicted to have unusual properties. Unlike ordinary particles, they might be able to undergo processes that involve faster-than-light effects. Some theorists have speculated that Majorana neutrinos could serve as carriers of information across vast distances through quantum entanglement networks that operate effectively instantaneously. These ideas remain speculative. No one has yet observed neutrinoless double beta decay. The process, if it exists, must be extremely rare, perhaps occurring only once per trillion years in a given nucleus. But the experiments are getting more sensitive every year. Detectors are being upgraded with larger masses and more careful shielding. The next generation of experiments coming online over the next decade will increase the sensitivity by orders of magnitude. If the process is seen, it will be one of the most important discoveries in physics. It will change our understanding of matter and antimatter. It will provide clues about why the universe exists at all, rather than being pure radiation. And it may open new windows into the nature of space-time itself. Neutrinos, those ghostly particles that slip through almost everything, continue to hold on to their secrets. And every experiment designed to catch them reveals another layer of mystery. They may be the most important key we have to understanding whether the speed of light is truly fundamental, or whether the universe has deeper rules we have not yet glimpsed. Some theorists have proposed an idea so strange it barely sounds like science. They suggest that the universe may be hollow, that the space we think is filled with matter and energy is actually a thin shell of reality wrapped around an unimaginable void, and that the speed of light is a property of this shell, not a universal truth. This idea is usually called the holographic principle. It was first proposed in the 1970s by physicist Gerard 't Hooft, and further developed by Leonard Susskind. The principle emerged from the study of black holes, but it has implications for the entire universe. The basic idea is mind-bending. Imagine a three-dimensional region of space like the inside of a room. Inside this region, there are atoms, molecules, perhaps even people. All the information about what is inside the room, according to the holographic principle, can be encoded on the two-dimensional boundary of the room. This is like saying that everything in a book can be described by the words printed on its cover. At first, it sounds absurd, but the mathematics of black holes and quantum gravity strongly supports the idea. If the holographic principle is correct, then the universe we experience might be a three-dimensional projection of information encoded on a two-dimensional surface. Everything we see, touch, and measure could be a kind of illusion, a shadow cast by a deeper reality. What does this have to do with the speed of light? In a holographic universe, the speed of light would be a property of how information is projected from the boundary into the interior. It would not be a fundamental constant, but a consequence of the projection process. And under certain conditions, the projection could break down, allowing information to move through the interior in ways that violate ordinary speed limits. Some physicists have argued that the faster-than-light anomalies observed in various experiments could be evidence of exactly this kind of breakdown. Quantum entanglement, for example, could be a case where the holographic projection is not fully hiding its underlying structure. Two entangled particles separated in space might actually be a single object on the two-dimensional boundary. What looks like instant communication between distant particles is really just the projection of a single piece of information into two locations. The holographic principle has gained significant support in theoretical physics. It has been rigorously demonstrated in certain mathematical models of gravity, particularly in something called anti-de Sitter space. Real experiments have shown signals consistent with some holographic predictions, though they are far from conclusive. If the universe is holographic, then our entire experience of space is an emergent phenomenon. Distance, volume, and the speed of light are all features of the projection, not of the underlying reality. Reality in this picture has fewer dimensions than we think, and the rules that govern our three-dimensional experience are not the deepest rules that exist. Some theorists have taken this even further. They have proposed that the universe is not just holographic, but fundamentally computational. Reality might be a vast information processing system, and what we call physics is the set of rules by which this system runs. In this view, the speed of light is simply the maximum rate at which information can propagate through the underlying computational substrate. If this substrate has parts that can communicate faster, those parts could produce the kinds of anomalies observed in quantum experiments. The universe might have built-in shortcuts that we are only beginning to detect. These ideas remain speculative, but they are taken seriously by respected physicists around the world, and they suggest that the speed of light may be just one feature of a much stranger reality. When astronomers look out into deep space, they are also looking back in time. Light from distant objects takes millions or billions of years to reach us. A galaxy, 1 billion light-years away, appears to us as it was 1 billion years ago. A galaxy 10 billion light-years away shows us the universe as it was when it was less than 4 billion years old. This gives astronomers a unique tool. They can study the history of the universe directly by looking at distant objects. And when they do, they sometimes find things that suggest the speed of light may not have always been what it is today. One of the most striking examples is the cosmic microwave background. This is the faint afterglow of the Big Bang, radiation that has been travelling through space for about 13.8 billion years. It fills the sky uniformly, with only tiny variations from one direction to another. The uniformity of the cosmic microwave background is itself a puzzle. Regions of the early universe that are now separated by billions of light-years appear to have nearly identical temperatures. Yet these regions were so far apart at the time, the radiation was emitted that no signal travelling at the speed of light could have connected them. They should not have had time to equalize their temperatures. This is called the horizon problem, and it has puzzled cosmologists for decades. The mainstream solution is called inflation. According to this theory, the very early universe underwent a brief period of incredibly rapid expansion, stretching space itself faster than light could travel. After inflation ended, the universe settled into its current, more sedate expansion. The uniformity of the cosmic microwave background was established before inflation, during a moment when all the regions were very close together. Inflation is widely accepted. It successfully explains the horizon problem and several other puzzles in cosmology. But it requires postulating a mysterious field, called the inflaton, that nobody has ever directly observed. And it raises the uncomfortable fact that space itself expanded faster than light during the inflationary epoch. Some theorists have proposed an alternative. Instead of space expanding faster than light, maybe the speed of light was much higher in the early universe than it is today. If light travelled much faster in the first instance after the Big Bang, it could have connected regions that now appear to be causally disconnected. The horizon problem would be solved without needing inflation. This idea is called variable speed of light cosmology. It was proposed by physicists like Magejo, who has written about it in his popular books. Magejo argues that a varying speed of light could solve several cosmological puzzles at once, including the horizon problem and the flatness problem. The idea is controversial. Most cosmologists favour inflation, but varying speed of light cosmology has not been ruled out, and some experiments are being designed to test it. If the speed of light was different in the early universe, it might have left subtle fingerprints in the cosmic microwave background, or in the distribution of galaxies. Preliminary searches have been inconclusive. The predicted effects are small and difficult to distinguish from other cosmological phenomena. But the search continues. If Magejo is right, then the speed of light is not a constant at all. It has been slowing down since the beginning of the universe, eventually settling into the value we measure today. This would be a dramatic revision of Einstein's picture, and it would raise new questions. What caused the speed of light to change? Is it still changing today? Too slowly to detect? Will it continue to change in the future? Not all physics breakthroughs happen at huge underground laboratories or on mountaintop observatories. Sometimes the most important experiments fit on a tabletop, and one such experiment, conducted in a small laboratory at the University of Maryland, may have caught the universe in the act of breaking its own rules. The experiment involved what physicists call an optical atomic clock. These are among the most precise timekeeping devices ever built. They work by measuring the frequency at which electrons in atoms oscillate between energy levels. The oscillations are so regular that modern atomic clocks can keep time to within 1 second over the age of the universe. In 2022, a team led by physicist Jun Ye set up 2 atomic clocks in the same laboratory. The clocks were placed at different heights on a lab bench, separated by about 1/5 of an inch. According to general relativity, the clock at a slightly higher altitude should tick slightly faster than the clock at a lower altitude, because gravity affects the flow of time. The effect is tiny. Across the height of a bench, the difference in tick rates is only about 1 part in 10 to the 18. To put that in perspective, if one clock ticked once per second, the other would need to tick for billions of years to fall behind by a single second. But atomic clocks can measure even tinier differences. The Maryland team successfully detected the gravitational time dilation between their 2 benchtop clocks. For the first time, general relativity was confirmed at sub-millimeter scales. This was already a triumph. But buried in the data was something unexpected. The relationship between the tick rate of the clocks and their altitude was not perfectly linear. There were small deviations, fluctuations that did not match the predictions of Einstein's theory. The deviations were at the edge of measurement precision. They could have been experimental noise, they could have been a hint of systematic errors, or they could have been a genuine signal of new physics. Some theorists got excited. They pointed out that deviations from general relativity at small scales might indicate the presence of unknown fields or forces that affect the flow of time. If time flows slightly differently than Einstein predicted, then the speed of light, which is defined in terms of time and distance, might also be subtly different. The Maryland results have not been confirmed by other experiments. They remain a tantalizing anomaly, one of many small hints that something might be missing from our current theories. But the experiment demonstrated something important. The scale at which we can test the fundamental laws of physics has reached sub-millimeter precision. We can now probe the tiniest departures from established theories in ways that were impossible just a few decades ago. This opens up new possibilities. If variations in the speed of light exist at very small scales, perhaps caused by quantum fluctuations of space-time itself, we might be able to detect them with the next generation of atomic clocks. Several research groups around the world are working on exactly this kind of experiment. They're building networks of ultra-precise clocks at different locations, comparing their tick rates in search of any anomalies. If the speed of light varies, even by tiny amounts, these networks should eventually detect it. The universe, it seems, does not give up its secrets easily. But we are building better and better tools to listen for whatever whispers it is willing to share. Physicists have long suspected that ordinary matter accounts for only a small fraction of what exists in the universe. About 5% according to current estimates. The rest is made up of dark matter and dark energy, mysterious substances that have never been directly observed. Dark matter is particularly puzzling. It has mass. It exerts gravity. It shapes the formation of galaxies, but it does not interact with light. It is invisible, undetectable through ordinary electromagnetic means. One popular theory proposes that dark matter is made of particles that interact only through a hidden force. Some versions of this theory predict the existence of a new kind of particle called a hidden photon. It would be similar to the ordinary photon, the particle of light, but it would interact with dark matter instead of ordinary matter. If hidden photons exist, they would open up a whole new kind of physics. They would be carriers of a force we have never directly observed, and depending on their properties, they might travel at different speeds than ordinary light. Some theoretical models suggest that hidden photons could travel faster than light in certain circumstances. They might use shortcuts through hidden dimensions. They might propagate through vacuum in ways that bypass the usual speed limit. Experiments are hunting for hidden photons in several different ways. Some look for them in beams of ordinary photons, searching for tiny oscillations between the two types. Others look for them in astrophysical sources, where large numbers of photons are produced. Still others look for them in precision measurements of electromagnetic fields, searching for subtle deviations from expected behavior. In 2023, a team at the Center for Axion and Precision Physics Research in South Korea reported intriguing hints of hidden photons in their data. The signal was weak, and the statistical significance was not enough to claim a discovery. But it was suggestive. Other experiments have reported similar hints over the years. None of them have been conclusive, but the pattern of small anomalies continues to build, pointing toward the possibility that hidden photons really do exist. If they are confirmed, it would mean that the universe has multiple types of electromagnetism. The ordinary photons we know would be just one kind of carrier of electromagnetic force. Others would exist in parallel, mostly invisible but occasionally leaving traces in sensitive experiments. The implications for the speed of light would be profound. If there are multiple kinds of photons, the speed of light might depend on which kind you're talking about. Ordinary light would travel at the familiar speed. Hidden light might travel faster, or slower, or under different rules entirely. This could explain some of the faster-than-light anomalies that have been observed. If a small fraction of ordinary photons occasionally convert into hidden photons, travel faster through some hidden realm and then convert back. They could appear to have violated the speed limit. The effect would be rare and subtle, exactly the kind of anomaly that has been showing up in quantum tunneling experiments and delicate optical measurements. The hunt for hidden photons is intensifying. New experiments are coming online at laboratories in Europe, America, and Asia. Detection technologies are improving rapidly. Within the next decade, we may finally know whether these ghostly particles are real. If they are, our picture of electromagnetism will need a major revision, and the speed of light, that fundamental pillar of modern physics, may turn out to be only one speed among many. At the National Institute of Standards and Technology in Boulder, Colorado, sits one of the most precise clocks ever built. It uses trapped ions of aluminum to measure time with accuracy that defies ordinary comprehension. It would take more than 30 billion years for the clock to gain or lose a single second. This clock has been used for experiments that probe the deepest features of physics, and one recent experiment produced a result so strange that scientists are still debating what it means. The experiment involved comparing two quantum clocks that were entangled with each other. When clocks are entangled, their tick rates become correlated in ways that cannot be explained by any classical signal travelling between them. The Boulder team showed that when one clock was moved to a slightly different height in Earth's gravitational field, the entangled partner clock instantly adjusted its tick rate as well. The adjustment happened faster than any signal could have travelled between the clocks. It appeared to be genuinely instantaneous. On one level, this is just quantum entanglement doing what quantum entanglement does. The correlations between entangled systems are supposed to be instantaneous. This has been demonstrated many times. But the Boulder experiment was different. It involved not just measurements of particle states, but actual physical quantities that flow from general relativity. The tick rate of a clock depends on the gravitational potential at its location. When the correlation between entangled clocks transmitted this gravitational information instantly, it suggested that gravity itself might propagate in ways faster than light, at least when mediated through quantum entanglement. This flies in the face of everything Einstein believed. General relativity is supposed to treat gravity as a local effect. Changes in gravitational fields should propagate at exactly the speed of light, forming ripples called gravitational waves. These waves have been directly detected by the LIGO observatories, and they travel at precisely the speed of light, as predicted. But the Boulder experiment suggested that when gravity is measured through entangled quantum systems, it behaves differently. The information about the gravitational field seems to jump across space in ways that do not match the usual gravitational wave picture. Some theorists have interpreted this as evidence that gravity has a quantum nature that has not yet been fully understood. For nearly a century, physicists have been trying to combine quantum mechanics with general relativity into a unified theory of quantum gravity. Every attempt has produced mathematical problems that no one has been able to fully resolve. The Boulder results may be a hint of what quantum gravity looks like. At the quantum level, gravity might not be a purely local effect. It might have faster-than-light aspects that only show up in very special experiments involving entangled systems. Other laboratories are trying to replicate and extend the Boulder findings. The experiments are extraordinarily difficult. They require combining the most precise clocks in the world with the most careful quantum control techniques ever developed. Only a handful of groups on Earth have the capability to perform such measurements. If the results hold up, they will force a major revision of our picture of gravity and space-time. The speed of light will remain an important boundary in ordinary physics, but at the deeper quantum level, The universe may operate by different rules entirely, rules that allow certain kinds of information and influence to travel instantaneously across any distance. This would not be a simple rejection of Einstein. It would be a refinement, a recognition that his theory is a beautiful approximation to a deeper reality, a reality where the speed of light is one rule among many, and where the universe has shortcuts we're only beginning to discover. Imagine a particle that can only travel faster than light, a particle for which the speed of light is a minimum speed, not a maximum. As you try to slow it down, it takes more and more energy, eventually requiring infinite energy to slow it to exactly the speed of light. This is the reverse of how ordinary matter behaves. Such particles are called tachyons. They were first proposed in the 1960s by physicists exploring the mathematical consequences of special relativity. Einstein's equations, when taken at face value, allow for particles with imaginary mass that must always travel faster than light. For a long time, tachyons were considered purely theoretical. They seemed to violate causality, allowing effects to precede their causes. They created paradoxes that made physicists uncomfortable. Most researchers assumed tachyons were mathematical curiosities that did not correspond to anything in the real world. Then, quantum field theory began producing hints that tachyon-like modes might actually exist. In certain theories, particles can acquire imaginary mass under specific conditions, producing behavior reminiscent of tachyons. The Higgs field, which gives mass to other particles, has tachyonic modes before it settles into its current configuration. The early universe, according to some models, was filled with tachyon-like fluctuations that shaped its subsequent evolution. More recently, some theorists have proposed that certain dark matter candidates might be genuinely tachyonic. Particles that exist in a separate sector of physics, barely connected to ordinary matter, but always moving faster than light. These would be invisible to most detectors, but might leave subtle fingerprints in astronomical observations. One experiment conducted at the Pierre Auger Observatory in Argentina has been looking for exactly these kinds of signatures. The observatory studies ultra-high energy cosmic rays, the most energetic particles ever detected from space. If tachyonic particles exist, they might interact with ordinary matter at very high energies, producing distinctive patterns in cosmic ray showers. So far, no clear evidence of tachyons has been found, but the search continues, and some of the anomalies observed in cosmic ray data have been interpreted speculatively as possible hints of tachyonic behavior. Other experiments are looking for tachyons in different ways. Particle accelerators are searching for them in high-energy collisions. Gravitational wave detectors are watching for unusual signals that could indicate tachyonic disturbances. Astronomical surveys are looking for patterns in the cosmic microwave background that might betray the presence of tachyons in the early universe. If tachyons are eventually confirmed, they would represent a fundamental revision of our picture of reality. The universe would contain a new category of matter, operating by rules that seem to defy common sense. Causality might need to be rethought. The flow of time itself might need to be understood differently. Some theorists have even suggested that tachyons could be used for communication. A tachyonic signal, if it could be generated and detected, would arrive before it was sent. This could theoretically allow for messages to be sent backward in time, with all the paradoxes that implies. Whether tachyons exist remains an open question. But the mere fact that serious physicists are hunting for them shows how far our understanding has come since Einstein first set down his speed limit. The idea of faster-than-light particles has moved from impossibility to possibility, and the universe may yet surprise us with what it contains. In 1935, Einstein and his colleague Nathan Rosen were exploring the mathematics of general relativity when they discovered something unexpected. The equations seemed to allow for shortcuts through space-time, tunnels connecting distant regions of the universe, passageways that could, in principle, be used to travel faster than light without actually breaking the speed limit. These structures are called Einstein-Rosen bridges. Today, they are better known as wormholes. For decades, wormholes were treated as mathematical curiosities. The solutions existed on paper, but they were unstable. Any attempt to send a particle through a wormhole would cause it to collapse. The passage would slam shut faster than anything could cross it. Then, in 1988, physicist Kip Thorne and his colleagues showed something startling. If you had a special kind of exotic matter, a substance with negative energy density, you could stabilize a wormhole and keep it open. Someone could then travel through it, from one end to the other, covering a cosmic distance in a short time. The catch was the exotic matter. No one had ever produced it. Quantum mechanics predicted that small amounts of negative energy could exist briefly in certain situations, but not the stable, controllable kind that would be needed to hold a wormhole open. For years, traversible wormholes remained firmly in the realm of science fiction. Then came a surprise. In 2017, physicists Ping Gao, Daniel Jafferis and Aaron Wall showed that wormholes could be stabilized using quantum entanglement. If you connected two black holes with an entanglement link, the resulting structure would be a traversible wormhole. The exotic matter was not needed. Quantum weirdness could do the job instead. This was a theoretical result. Creating entangled black holes is beyond any current technology. But the discovery opened the door to new ways of thinking about wormholes and faster-than-light travel. In 2022, a team using Google's quantum computer claimed to have simulated a small wormhole-like system. They created a simplified version of the Gao-Jafferis Wall construction in a quantum circuit and observed behavior consistent with information traveling through a wormhole. The claim was controversial. Some physicists argued that the simulation captured the essential features of wormhole physics. Others argued that the system was too simplified to really count as a wormhole, and that the observed behavior could be explained by ordinary quantum mechanics without any geometrical shortcuts. The debate continues. But the experiment demonstrated that wormhole physics is no longer purely theoretical. Simplified versions can be explored in laboratories, at least in principle. If real traversible wormholes exist in the universe, they could connect distant regions of space in ways that effectively allow faster-than-light travel. A ship entering a wormhole at one end could emerge at the other end, millions of light-years away, in a matter of moments from its own perspective. From the outside, it would appear to have violated the speed of light, even though it never actually did. Some astrophysicists have speculated that wormholes might occur naturally in the universe. They could form from collapsing stars under unusual conditions. They could be left over from the Big Bang. They could be artifacts of quantum gravity processes that we do not yet fully understand. Searches for natural wormholes have so far come up empty. If they exist, they are either rare or well hidden. But the theoretical possibility remains, and it represents yet another way that the universe might circumvent Einstein's speed limit. The space between galaxies might not be as empty or as rigid as it appears. Shortcuts might be woven into the fabric of space-time, waiting to be discovered. In 2004, astronomers studying the cosmic microwave background noticed something strange. In a particular direction in the sky, there was a region that was significantly colder than the surrounding areas. The temperature difference was small, about 70 microkelvin, but it was large enough to stand out against the background. This region is called the CMB cold spot. It covers an area about 5 degrees across in the sky and extends over a vast distance in the early universe. Its discovery touched off a debate that has raged for nearly 2 decades. At first, the cold spot was thought to be a statistical fluke. The cosmic microwave background has small variations everywhere, and occasionally a particularly large variation will appear by chance. But as astronomers studied the cold spot more carefully, it began to seem increasingly unlikely to be random. The temperature of the cold spot was too low, too extensive, too unusual to be explained by ordinary fluctuations in the early universe. Something had produced it, and the standard theories could not say what. One proposal was that the cold spot marks the location of an enormous cosmic void, a region of space with far fewer galaxies than the average. When light passes through a large void, it loses a small amount of energy due to the expansion of space during its transit. If the cold spot corresponded to a giant void, it could explain the temperature dip. In 2015, astronomers led by Istvan Shapudi reported finding a massive void in roughly the right direction, a region of space about 1.5 billion light-years across with significantly fewer galaxies than surrounding areas. This seemed to support the void hypothesis. But the match was not perfect. The void was real, but it was not quite large enough or empty enough to fully account for the cold spot temperature. Some of the temperature anomaly remained unexplained. This led to more exotic proposals. Some theorists suggested that the cold spot might be a cosmological bruise, evidence that our universe had collided with another universe in the multiverse. Others proposed that it might mark the location of a topological defect, a kind of cosmic string or domain wall left over from the Big Bang. A particularly provocative idea is that the cold spot could be evidence of faster-than-light propagation of disturbances in the early universe. If some kind of signal had travelled faster than light during the first moments after the Big Bang, it could have produced exactly the kind of localised temperature variation seen in the cold spot. This would require the speed of the light to have been different in the early universe, consistent with the varying speed of a light cosmology we discussed earlier. Or it would require some other mechanism for superluminal propagation, perhaps involving extra dimensions or exotic physics that has not yet been understood. The cold spot remains unexplained. Multiple theories compete to account for it, but none has gained clear acceptance. More detailed observations in coming years, particularly from new space-based telescopes, may help resolve the mystery. Whatever caused the cold spot, it represents a genuine puzzle in cosmology. The early universe seems to have contained features that standard theories cannot produce. Something happened in those first moments that left fingerprints we can still see today, 13 billion years later. And those fingerprints might be evidence that the rules of physics were different back then, or that the universe has hidden mechanisms we've not yet uncovered. At the Large Hadron Collider near Geneva, the most powerful particle accelerator ever built, physicists have been conducting experiments that probe the deepest levels of matter. Among the many particles produced in the collider's high-energy collisions, one has received particular attention for its unusual behaviour. The particle is called the bottom quark. It is one of 6 types of quarks, the fundamental building blocks of protons and neutrons. Bottom quarks are heavy and unstable, decaying rapidly into lighter particles. By studying exactly how they decay, physicists can test the predictions of the Standard Model with extraordinary precision. And in recent years, the bottom quark has been misbehaving. Experiments at the LHCb detector, a specialized facility within the Large Hadron Collider complex, have found that bottom quarks decay into muons and electrons at rates that do not quite match predictions. The differences are small, a few percent, but they are statistically significant. This kind of anomaly is called a lepton universality violation. The standard model predicts that bottom quarks should decay into different kinds of leptons at rates determined only by the masses of those leptons. There should be no intrinsic preference for one type over another. But the LHCb data suggests that the bottom quark actually does show preferences that the standard model cannot explain. If confirmed, this would be evidence of new physics beyond the standard model. There would have to be a force or interaction that preferentially affects different kinds of leptons in ways we've not yet discovered. Some theorists have proposed that the culprit might be a hypothetical particle called a leptoquark. This is a particle that would interact with both quarks and leptons, potentially creating exactly the kind of asymmetry observed at the LHCb. Leptoquarks are interesting for many reasons, but one particularly intriguing possibility is that they could be associated with hidden dimensions or new forces that do not respect the usual speed of light limits. If leptoquarks exist and they mediate interactions that can travel through hidden dimensions, they could create shortcuts in the particle world, analogous to the wormholes we discussed in the previous chapter. Several experiments are now hunting for direct evidence of leptoquarks. The searchers have not yet found them, but the energy levels being probed are higher than ever before. If leptoquarks exist below a certain mass, they should be observable in the next decade of LHC operations. Meanwhile, the anomalies in bottom quark decays continue to be studied. Recent updates have shown some tension with the original findings. Some of the anomalies have weakened as more data has been collected, while others have remained. The situation is complex and a clear picture has not yet emerged. But the pattern is familiar. Whenever we look carefully enough at any corner of physics, we find small anomalies that the standard theories cannot quite account for. The bottom quark deviations, the muon wobble, the neutrino oscillations, the pioneer drift, the flyby anomaly, the cold spot, the faster-than-light measurements in various optical experiments. Individually, each anomaly might be dismissed as an experimental artifact or a minor theoretical oversight. But collectively they paint a picture of a universe that is slightly different from what our theories describe. A universe with subtle deviations from the standard model and general relativity. A universe that might be sending us messages we are only beginning to decode. The question is whether these messages will eventually coalesce into a new paradigm, or whether they will fade back into statistical noise as measurements improve. Only time will tell. But the searchers continue, following the hints wherever they lead. For over a century, physicists have dreamed of a single theory that would describe every force and every particle in the universe. A theory of everything. Einstein spent the last decades of his life searching for one, without success. Since his death, generations of physicists have continued the hunt. The main obstacle has been the clash between two extraordinarily successful but incompatible theories. General relativity describes gravity and the large-scale structure of the universe. Quantum mechanics describes the behavior of particles at the smallest scales. Both theories work beautifully in their own domains. But when you try to combine them, you get mathematical contradictions and impossible predictions. String theory has been the most ambitious attempt to unify them. In this theory, the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings. Different vibrations correspond to different particles. The theory naturally incorporates both gravity and quantum mechanics, and it predicts the existence of extra dimensions beyond the four we experience. String theory has been enormously fruitful mathematically. It has led to new insights in physics and mathematics alike, but it has failed to produce specific testable predictions that could be verified by experiment. Critics have called it untestable, a beautiful mathematical construction without empirical content. Recently, a different approach has been gaining ground. It is called loop quantum gravity, and it takes a different path to unification. Instead of adding extra dimensions, loop quantum gravity proposes that space-time itself is made of tiny quantum units. Space would not be continuous but granular, like the pixels in a digital image. Time would come in discrete ticks rather than flowing smoothly. In this picture, the speed of light emerges from the structure of the quantum space-time. It is not a fundamental constant, but a property of how information can propagate from one pixel of space to the next. And under certain conditions, the speed could vary. Loop quantum gravity predicts that very high-energy photons should travel at slightly different speeds than low-energy photons. The effect is tiny, but it could accumulate over cosmic distances. If a burst of photons is emitted simultaneously from a very distant source, the high-energy photons should arrive at Earth slightly before or after the low-energy photons. Several observations of distant gamma-ray bursts have been used to test this prediction. So far, no significant energy-dependent time delays have been observed. This puts constraints on certain versions of loop quantum gravity, but it does not rule out the theory entirely. Another approach, called causal set theory, proposes that space-time is made of discrete events connected by causal relationships. In this picture, the speed of light is the natural consequence of how these causal connections propagate. And like loop quantum gravity, causal set theory predicts subtle deviations from Einstein's rules at very high energies or very small scales. Other approaches to quantum gravity include causal dynamical triangulations, non-commutative geometry, and asymptotic safety. Each proposes different ways of unifying gravity with quantum mechanics. Each makes different predictions about the deep structure of space-time. None of these theories has yet been confirmed by experiment, but the search for a theory of everything continues, and whatever the correct theory turns out to be, it will almost certainly change our understanding of the speed of light in some fundamental way. Einstein's speed limit was a breakthrough of the early 20th century. The next breakthrough, when it comes, will likely show that this limit is a consequence of something deeper, something we're only now beginning to glimpse through the mists of theory and experiment. Plans are already underway for experiments that will test the foundations of physics with precision far beyond what is currently possible. These projects represent the cutting edge of human scientific ambition. If they succeed, they may finally resolve the anomalies that have been piling up for decades. The largest of these is the Future Circular Collider, a proposed successor to the Large Hadron Collider. It would be a ring of superconducting magnets about 55 miles in circumference, buried deep beneath the countryside near Geneva. Particles would be accelerated around this ring to energies 7 times higher than anything achieved before. At these energies, entirely new particles might become visible. Hypothetical particles like leptoquarks, sterile neutrinos, dark matter candidates, and the elusive graviton could all potentially be detected. The collider might also produce tiny quantum black holes, which would evaporate almost instantly, but could reveal the deepest secrets of space-time. If the Future Circular Collider is built, it will begin operation around the year 2040. It will cost tens of billions of dollars, require thousands of scientists, and take decades to complete. But if it succeeds, it could provide the first direct experimental evidence for new physics beyond the standard model. Other proposed experiments focus on different aspects of the mystery. The Einstein telescope, planned for construction in Europe, will be a gravitational wave detector far more sensitive than existing instruments. It will be able to detect gravitational waves from almost every part of the observable universe. If gravity violates Einstein's predictions in any subtle way, the Einstein telescope should be able to see it. The Deep Underground Neutrino experiment, already under construction in South Dakota, will track neutrinos fired 800 miles through the Earth. It will measure neutrino oscillations with unprecedented precision and may finally determine whether sterile neutrinos exist. Space-based experiments are also in development. The Laser Interferometer Space Antenna, a trio of satellites that will form a gravitational wave detector millions of miles across, is scheduled for launch in the 2030s. It will detect low-frequency gravitational waves that are invisible to ground-based detectors, opening a new window on the universe. Atomic clock networks are being established around the world. These will compare time at different locations with extraordinary precision, searching for subtle variations that could reveal hidden physics. Networks of quantum sensors will probe the vacuum for unexpected properties. New telescopes are being designed to study the early universe in unprecedented detail. The successor to the James Webb Space Telescope is already on the drawing board. It will look farther back in time, gathering more light from more distant galaxies. It may finally reveal whether the speed of light was different in the early universe, or whether the cosmic microwave background cold spot has a natural explanation. All of these experiments share a common goal. They seek to test the foundations of physics more rigorously than ever before. They seek to confirm or refute the many anomalies that have accumulated over the past few decades. They seek to determine whether Einstein's speed limit is truly a universal law, or whether it is just an approximation to a deeper reality. Within the next 2 decades, many of these experiments will begin producing results, and those results will either strengthen Einstein's theory or reveal its limitations. Either way, we'll know more than ever before about the structure of the universe. The answers are coming, and they may change everything. We began this journey with a simple claim. Physics ran experiments on light speed, and the results do not quite add up. Over these 33 chapters, we have explored the many ways in which Einstein's speed limit may be showing cracks, anomalies in neutrinos and muons, faster-than-light tunneling of photons, quantum entanglement that defies distance, cosmological puzzles that hint at varying constants, black hole paradoxes that point to missing physics. Most of these anomalies remain unexplained. Some have been shown to be measurement errors or misinterpretations. Others have survived rigorous testing. None of them has yet produced a definitive break with Einstein's theory. But together, they suggest that our understanding of light and space is far from complete. The question at the heart of this investigation is not whether the speed of light is a real limit. In ordinary circumstances, it clearly is. Every test of special relativity in ordinary conditions has confirmed Einstein's theory to extraordinary precision. If you throw a ball, send a signal, or launch a rocket, nothing will exceed the speed of light. The question is whether this limit is truly fundamental, or whether it is a feature of the specific regime we happen to live in. Under extreme conditions in exotic setups, at the smallest scales or the largest, the speed of light might not hold its grip as firmly as it does in everyday life. This question matters enormously. If the speed of light is a deep universal constant, then humans are forever bound to travel between stars at painstakingly slow speeds, if we can travel between stars at all. The nearest star system, Alpha Centauri, is over 4 light-years away. Even at a fraction of the speed of light, a journey there would take many human lifetimes. But if the speed of light is not truly fundamental, if there are shortcuts through extra dimensions, or wormholes linking distant regions, or quantum mechanisms that allow for faster-than-light communication, then the universe may be far more accessible than we have imagined. Our descendants might travel between stars in months rather than millennia. We might communicate with civilizations across the galaxy. We might become a cosmic species in ways that are presently unthinkable. Beyond practical considerations, the question touches on our deepest understanding of reality. If the speed of light is not absolute, then space and time themselves are not absolute. Causality as we know it may be a feature of our local environment rather than a universal law. The past and future may not be as separate as we think. The universe may be connected in ways that our classical intuitions cannot grasp. Some physicists find these possibilities exhilarating, others find them disturbing. Most reserve judgment until stronger evidence emerges. The anomalies we have explored are hints, not proofs. They point toward the possibility of new physics without confirming it. They are puzzle pieces that may or may not fit together into a larger picture. Over the coming decades, experiments will probe these anomalies with ever greater precision. New theories will be proposed and tested: the Future Circular Collider, the Einstein telescope, space-based detectors, atomic clock networks, and telescopes peering into the deepest past will all contribute to the search. Some anomalies will be resolved as measurement errors, others may grow into undeniable evidence of new physics. The universe has not finished revealing itself. Einstein gave us an extraordinary picture of how light and space work. But he himself hinted that deeper truths might lie beyond his theory. 100 years from now, textbooks may describe our era as the time when humanity first began to glimpse those deeper truths. Or they may describe our anomalies as false alarms, reminding readers that Einstein was right all along. Either way, the journey of discovery continues, and the speed of light, that most famous of cosmic speed limits, remains one of the most fascinating mysteries in all of science.